Okay? So again, an atom or group, notice it says group of bonded atoms that have a positive or negative charge. What are the positive ones called? What are they called? Nope. Cations. What are the negative ones called? Anions. So cations and anions. And I showed you this, right, people? Didn't I show this to you? Right? Positive, negative. Okay? So don't forget that. All right. So let's look at some. Here's one, Na+. So the way we say this is it's really easy. We just say the sodium cation. Okay? So we just add the word cation after it. Here's another one, Cl-. This is a little different. We don't say chlorine anion. We don't say that. We say chloride anion. So we add this IDE ending, okay? IDE ending. Chloride anion. That's why it's not called sodium chlorine, it's called sodium chloride. Okay? Okay. Let's move on to this one, NH4+. Okay? NH4+. Notice this is a group of two elements now. This is known as the ammonium cation. People ask, where does the ammonium come from? It comes from the fact that NH4+ comes from something called ammonia. That's ammonia. So you add a hydrogen, so you make ammonium cation. Okay. And this last one here is SO3 2-. We call that a sulfite anion. Both of these are on the back of your periodic table in the ions chart. They talk about these two. Okay? These are called, people, and you need to write this word down, polyatomic ions. Okay? Polyatomic ions. Okay? Polyatomic ions. So we'll learn more about this, but this usually becomes difficult, a little bit more difficult for you. But I mean, one way to think about it is an SO3 2-. When you start making other compounds with it, it's like a family. They travel together in a pack and they never separate. SO3 2-, you treat no differently than O2- or S2- or Te2-. It's just a group of things that come bundled together as a 2-. Polyatomics. Okay? So, any process that creates an ion is referred to as ionization. Okay? Any process that creates an ion is referred to as ionization. So we're going to talk about the trend of ionization and what that means. So the first thing here is ionization energy. And write this down, but it's the energy required to take an electron away from an atom. So it's like, how easy is it to take an electron away? Like fluorine is up here. Fluorine's all like, I want electrons, I want electrons, I want electrons, I want electrons. Then someone says, I need to take an electron away from you. And fluorine's like, I don't think so. It's not going to happen. Sodium, on their hands, like, want my electron? Okay? Basically. Okay? And then fluorine's like, sure. But this is the energy required to just take an electron away. So you might imagine something like fluorine, it's really hard to take an electron away from it if it's trying to get electrons. Likewise, sodium wants to become, right, sodium wants to lose its electron and go, follow me on the periodic table. Sodium's up here. It wants to lose its electron and become like neon. You can imagine it's not going to be very hard to remove its electron, so it won't take as much energy to remove it. Okay? It turns out that these energies trend on the periodic table. So write this equation down, but what energy is required to add to an element to make a cation and an electron? Okay? To remove an electron. Okay. And for main group elements, ionization energy increases across the period. So that means as you go this way, ionization energy increases. As you go down, the ease at which an electron is removed becomes easier. So it takes less energy. And actually, if you think about it, you saw that today. I took sodium, right? I took a chunk of sodium that's the same size as a chunk of potassium. I threw that into the water and did nothing, right? It reacted. But then I took that same potassium, chucked it in the water, and it reacted even more. So it seems like potassium was much more willing to give up its electron quicker than sodium. So it took less energy to get this reaction to go more vigorously. So it would seem as ionization energy gets less as you go down. Okay? So I'll show you guys that chart, and there's a chart. It's like a little 3D chart. Kind of shows this. Hydrogen's a little bit of an outlier. Got to be careful. Okay? But look at it. Cesium. Look at it. It takes a lot less energy to remove an electron from potassium than sodium. That's why potassium is more reactive. You can see fluorine's up here going, yeah, I don't think you're going to take my electron away. And this right here shows you why the noble gases are noble. They're stable already. They don't want to give up an electron. So it's going to take a lot more energy to remove their electrons. Okay? So keep that in mind. There's a few places where the trend is a little disturbed here, but we're not going to get it too much in that. But the general term is ionization energy increases this way, and ionization energy increases this way. So they end up getting high over up here and low down here. Isaiah.
What about like francium and other elements?
Francium is just, this table just doesn't have, francium will be even lower. It'll be right here, okay? So this doesn't have calculated values. This is actually calculated values. They skip the transition metals. The reason you don't have francium is probably because they didn't have a sample to actually test. At any one time on the planet, it's estimated that there's only 20 atoms of francium. It's a highly unstable element, okay? So idea would be you couldn't actually test that, okay? So what determines ionization energy? The greater the nucleus charge, the greater the IE. So as you go across the periodic table, you add more and more protons, and so they hold on to those electrons a little bit more tightly. So you need more energy to pull them away, okay? And when you go down, you're just that much further. Your cesium, you're going to see tomorrow how explosive cesium is. You're going to see, hey, I'm so far away from the nucleus, who cares? I'm going to go hang out with this water molecule, see what happens. I don't need to go home to the nucleus. I'm hanging out here. So you're farther away, you're more apt to, get in trouble, do things, right? When you're sodium, you're much closer to the nucleus. So the further you are away, those outer electrons that we talked about, those valence electrons are held much less loosely, and so they don't need as much energy to pull them away. Okay? You could think of almost like planets as well. It's probably be a lot harder to pull Mercury away from the sun than it would be to pull Pluto away. Right? Pluto's hanging way out there. Probably not much to pull it away. Okay? Now we're going to talk about electron affinity. And this is the energy produced when an electron is added to a neutral atom. So it's the exact opposite of ionization energy. Now we're going to see how much energy an element gives off when we throw an electron at it. Isaiah.
Is there any correlation to
The ionization energy, think about this now. It's less, as you move down, the atoms get bigger, right? And as you move down, the energy required to remove an electron becomes less. That's because the atom got bigger, and now the electron's further away, so it's much easier to pull it off. Does that make sense from the nucleus? Okay? So yes, there is absolutely a correlation with atomic size. Okay? So this is the equation. What if we try to just jam an electron into an element and make A minus an energy? This is kind of difficult for some elements like sodium. Sodium's sitting over here going, do you want my electron? Do you want my electron? And then someone comes like, here, have another electron. Sodium's like, what? I'm trying to get rid of my electron to become like neon. I don't want another electron. Meanwhile, fluorine's over here. Fluorine just needs one electron to become like neon. So it sees you coming along and says, gimme, 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 gimme. It's like my dog, ball, 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 ball. You know, same thing. Fluorine's like, give me an electron. Okay? So electron affinity means that the energy that it will give off to get, in other words, fluorine will be willing to pay you energy to get that electron. Okay? So let's look at that a little bit. So here's a table. And if you look at it, never mind the negative signs, but to some extent you see that fluorine and chlorine are both very high numbers and they have a high electron affinity. You see sodium and lithium in these guys. They don't really want anything. And again, the noble gases, they don't want electrons. They don't want to give up electrons. They're in a good place. Why would you want to change anything if you're the king or the queen? Yes?
Why does magnesium not have anything?
Why? Oh, right here? Good question. There's definitely some of these trends which you'll see is that they're not quite, there's always a little bit of subtleness in them. So I don't exactly know, for instance, why, but again, you're trying to add an electron to magnesium, and magnesium wants to give up 2 electrons. So it might kind of make sense that perhaps it's just like, okay. My guess is most of the main group elements are similar. They just don't hardly have any electron affinity whatsoever. They're all cations. All of these through here are cations. All of these are cations. These are the only anions. Okay. Let's talk about electronegativity. So electronegativity is really probably the most important concept you'll get out of this lecture. And electronegativity is a lot like electron affinity, but it's a lot better because there's not some of these inconsistencies like Simon pointed out magnesium and those ones, or why does chlorine have a higher electron affinity than fluorine? Electronegativity is a calculation, and it's a real simple measurement. It's a measurement of how much an atom can attract electrons. Okay? And what's beautiful about this is it kind of runs from a scale of 1 to 4. 1 being not very much, 4 being a lot. Okay? And the higher the number, the higher the electronegativity. So if you get a number near 4, that means the element has a higher electronegativity. If you get a number around 1 or a little bit below, it means it has a low electronegativity. Okay? And so these values change a little bit. People publish different things, but kind of these are the accepted values. Sometimes you see francium as 0.9. Some of these numbers aren't measured. They're actually calculated. But fluorine is given sort of the top dog. It's given a 4.0. And francium is down there around 1 or so, maybe even a little bit below 1. Okay? This table will be really important in the next couple of chapters. I'll constantly ask you what the electronegativities are. Okay. I actually pretty much know the electronegativities by heart. Like I could tell you, let's test me right now. Hydrogen 2.1, carbon 2.4, chlorine's about 3.5. Remember those numbers? I said chlorine 3.5, I said carbon 2.4. Oh, I got to do this part first. We'll get to it. Proposed by Linus Pauling, okay? Useful in describing properties of compound. Here's Linus Pauling himself. He lived to be over 100. He's the only person to win a Nobel Prize in biology and chemistry. he actually proposed this idea of having mega doses of vitamin C. So he used to eat about 60 grams of vitamin C a day, which is like about 120 of those vitamin C tablets. He said it would extend your life. He lived to be pretty old. I'm not saying, but it's what we call anecdotal information. But he was a really brilliant chemist for probably about 6 decades. Okay. So let's look at it. You want to see the electronegativity chart? Yes, no, 3D, there it is. I said 2.1, oh, I said 2.4, it says 2.5. I said oxygen was 3.5. Oh, ooh, that's a little off. I forget. But what it shows you is that most of this stuff, yeah, fluorine in here, this says 4.1. It kind of moves around. Different people say different things. But, you know, I always think of 1 and 4. That's the best way to think about it. And again, it shows you this nice trend. Francium low, doesn't want electrons. Francium wants to blow up and give off its electron. Fluorine would really like to have an electron. And so would some of these other elements here, okay? It's not a surprise that this is where most chemistry takes place on the periodic table. The elements with the highest electronegativity. They want electrons, okay? So I want you to have an idea of the general trend. So what's the trend? Electronegativity increases that way, and it increases this way. The same as electron affinity, okay? Yes?
Why do any of the noble gases have... Oh, wait.
They're not even on there. Because they're like, I'm set. I don't need nothing from you. Leave me alone. Okay? So let's look at trends on ionic size. This is on page 175 and 76 of your book. But we'll just talk about it. Turns out that if you make an Na plus cation, it's actually smaller than sodium. Its parent atom. Kind of makes sense, right? Here's sodium. Remember when we did the thing with the 3s shell, and the 3s shell went over all the p orbitals? You guys remember that? The big gray, when I did the pictures? Well, look what happens. When you lose an electron from sodium, you go back to neon, you lose the 3s orbital. So Na plus is smaller than Na. It loses the 3s orbital. Okay? Likewise, anions are larger. They add an electron. The electron cloud gets bigger, so they're larger than their parent atoms. Okay? That's really all I want you to know about these two, okay? Is that cations are smaller than their neutral atoms and anions are bigger than their neutral atoms. Here's a picture. Here you can look at it in your leisure, but it shows sodium losing an electron and how it gets smaller. It shows fluorine gaining an electron and how it gets a little bit bigger. When it gains its electron, it becomes F minus. Okay. Okay, I think I got one slide left maybe at the most. So here's sort of a picture. You don't have to memorize this. But it's just showing trends on ionic size and things like that. The differences between rubidium and rubidium plus and things like that. And this one I don't need you to pay too much attention to. So let's go to here, putting it all together. Okay? So where it says electron affinity, you could also write electronegativity. And it's really, see if that works. Electronegativity. So you can, electronegativity, electron affinity, you could also write electronegativity here. So you see all these electronegativity, electron affinity, ionization energy all increase here and here. Atomic radius. Where it says atomic radius, you can also put ionic radius. So for the ions, it's the same, ionic radius for both here and here. Okay, ionic. So basically these two go this way. Note the metallic things are kind of more metallic this way, and they're more non-metals this way. So fluorines and helium are your ultimate non-metals, okay? That's basically it. I have a homework, it's due tomorrow, it's number 45. It's more of these periodic trends right here, okay? One sheet, it actually sort of arrange elements in order. This is a good study because a lot of questions in the test are similar to this, kind of conceptually. I think it's actually good practice. We will have a test on chapter 5 and 6 on Friday. Okay. So put 45, assignment 45, due tomorrow. Now, I still have homework to check, and I only got 1 minute, right? I didn't check homework, so I'll check both of those tomorrow as well. We spent longer on the demo. First period never asked a question either. They're too busy sleeping. So I'll check homework 44, so if you didn't do it, and 45 tomorrow, okay? And we'll do a review tomorrow, like a money review, and some chem dollars. And then we'll have a lab on Wednesday, Thursday.
Scott.
And then
Rolls
test
on
Friday.
rolls. Or scrolls.
Yes. French toast.
Chris.